So, in the last lecture, we defined these different characteristics, right? So, the rise time, settling time, the peak time, and the percent overshoot. Those were the four that we defined. And they're defined for all kinds of systems. They don't have to be of a certain order. But we can solve for these parameters exactly in first and second order systems without zeros. Well, we'll talk more about exact. In the first order case, we can do it exactly. In the second order case, you have to do a little bit of a numerical solution to get it in closed form, because it's nonlinear as hell. So we'll talk about that. Okay. First order systems without zeros. It's like the really nice. Oh man, look at this. I like this. I feel like FRST for first. It's like my thing now. Okay, first order system without zeros has a transient response characterized by a time constant, tau, that appears in the total response as this. So there's some term times e to the minus t over tau plus some other term. So this is really familiar. We've done this like a bunch of times, right? First order system, we solve, characteristic equation. We get that there's only one solution for lambda, roots of the characteristic equation, and that gives us the time constant tau. And then we have our homogeneous solution, and then we can find the particular solution by the form of the input. And then we could add those two together to get the total solution. Then we could apply the initial conditions to get the specific solution. Is this sounding familiar? I hope. Oh, guys. Okay, so this is very familiar. We have this decaying exponential response for a first order system, right? We've solved for it like a jillion times, and we're kind of getting tired of it, to be honest. The transient exponential decay, such that in the transient exponential decays such that in 3 time constants, 3 tau, only 5% of the term remains. In 5 tau, less than 1%. So this term, after 3 time constants, there's only 5% of it left. After 5 time constants, there's less than 1% of it left. Okay? Because this exponential is just getting smaller and smaller and smaller, right? E to the minus larger and larger number gets smaller and smaller and smaller. Exponentially so, in fact. Okay. There is neither peak nor overshoot for this type of response. However, the rise time for these systems is found by solving the time domain differential equation. So this is the differential equation that governs a first order system with no zeros, okay? We know there are no zeros because we have no time derivatives of the input u, right? With output variable y, input variable u, and real constant k, it is easily shown that the solution to equation 3.2 is 3.3, right? So this is the solution when you go through it. And it's an exponential that decays from 0 to some steady state value k, right? That's the solution. From which we discover that the steady state value is taking the limit as time goes to infinity. This exponential goes to 0. So we have k times 1 left, so we have k as the steady state solution. The rise time is, by definition, the duration of the time interval, t1 to t2, such that y of t1 is 10% of the steady state and y of t2 is 90% of steady state. That was the definition we used in last lecture. So the first of these, if we just plug that in, yields solving for what time that occurs. So we say this solution, we want to know when it reaches 0.1 times the steady state. So we just plug that in. 0.1 times the steady state, which is k, equals the solution. And we can solve for the time at which that occurs, t1. All right? So that's one side of our interval, right? So we found t1. It's about 0.1 times tau, approximately. Solving in an analogous fashion, we find T2. So you can do the same exact thing, except for you set it equal to, instead of 0.1k, 0.9k, and solve again, and you get that T2 is about 2.3 tau. The interval then is the difference between those two, which is 2.1972 tau. So our rise time I'll do it approximate. T rise is approximately equal, for a first order system, tau times the natural log of 9, which is equal to, well actually, I'll make this one exact. This one is actually exact. Tau times the natural log of 9, and this is approximately equal to 2.2 tau. We approximate 2.1972 to be 2.2. So when you have a first order system and you know it's time constant, you multiply that by 2.2 and that's its rise time approximately. So it's kind of nice. Finally, the settling time can be derived in a fashion similar to the rise time. So you have to define when it reaches 98%, right? This thing's never going to leave that plus or minus 2% band. So once that response reaches 98%, it's within 2% of the final value, and then you can solve for what time that occurs. And so it's essentially the same procedure. And we find that the settling time is equal to negative tau times the log of 0.02, which is approximately equal to 3.9 time constants. So first order system has a settling time of 3.9 time constants. Sometimes people say 4 time constants because, you know, it's close to 4. So this is the first order settling time. So for the first order system without zeros, we solved exactly. So the time constant gives us both the rise time and the settling time. Not super eventful though, right? This first order system, this is not a lot going on. Second order systems without zeros are a little bit more involved. Second order system transient responses are characterized by a natural angular frequency, omega n, and damping ratio, zeta. It is helpful to recall the complex plane graphical representation of the pole zero plot for a second order system without zeros, as shown in 3.2. So remember, if you have your poles in the left half plane here, this is the S plane, the complex plane, right? If our poles are in the left half plane, then we have a stable system. But also it governs the transient response of a system. And so we're going to get really used to seeing this S-plane representation of the poles and the zeros. Okay? Pole zero plots are going to be really, really helpful for us in the near future. So we have a complex conjugate pair of poles, no zeros. This is for the no zero second order case. So there's 2 poles, and there's 2 of them here, so it's a second order system. And we have several parameters that you can just kind of like read off of this complex representation, okay? So let's try to remember what they are. So if you start up here, remember this is zeta equals 0, right? There's no oscillation, or there's oscillation but no damping at that point. And the height of it is actually the natural frequency. But it turns out that the entire arc has radius of the natural frequency, omega n. So even if it's when it's underdamped, it has a radius from the origin of omega n, which is an important characteristic. So anytime you follow a circle around the origin, you're at constant natural frequency, which is kind of cool. Okay, let's look sort of geometrically at what happens if you have zeta greater than 1. So this is what happens if you have an overdamped system. The complex conjugate pair of poles become real, right? So they're not complex anymore. So this is zeta greater than 1. And then right here is this critical damping, right? So this is zeta equals 1. This is when it's almost going to oscillate, but it's not quite. And this is where you have this double pole there. And then when we start decreasing the damping, we have zeta between 0 and 1 along this. So this is zeta decreasing to 0, right? Zeta starts at 1 and decreases to 0 along this arc. And in fact, it turns out that the angle that it has between the negative real axis and the ray going through the pole is the arc cosine of zeta. So if you know that angle, you know zeta. Or if you know zeta, you know that angle. So we see the zeta starting at 1 here, and along this arc it is decreasing. And another interesting fact about that is that at a certain angle, no matter what the natural frequency is, no matter what the radius is, you're at a constant damping, right? So that means that if you follow a ray from the origin out, any ray, a pole anywhere along that ray is going to have the same damping ratio. So that's an interesting aspect of this. Yeah, those are the highlights. This is actually equal to the damped natural frequency, so which is the natural frequency times square root of 1 minus zeta squared. Zeta squared. So those are the highlights of looking at this complex conjugate pair of poles, or it could even be that they turn real. And then anything that's over here in the right half plane, we would say is zeta is greater than 0. Sorry, less than 0, negative, right? The positive real part. Unstable stuff is over there. Okay, good. Following a procedure very similar to that of first order systems, the following relationships can be derived. The rise time does not have an analytical solution in terms of omega n and zeta. However, figure 3.3 shows numerical solutions for the rise time scaled by omega n for zeta between 0 and 1. So this figure is actually, like, I included on it, they're pretty light, so you definitely can't see them up there, but hopefully in your printout you can see them okay. There are grid lines on it. You still can't see it on the screen. There are grid lines on it because this is actually, like, legitimately one of the few graphs that I recommend you actually read values off of. Used to be standard in engineering, you would read stuff off of graphs all the time. This one you can come up with, like, I wrote the MATLAB script that solves for this line, so you could have a numerical solution for it. But it's a little bit involved, takes a little bit of work. I mean, it doesn't take very long, but it's not something that you can solve for easily with any technique other than a numerical solver. Okay, so there's no formula to plug into to find this. So this is actually legitimately what I expect you guys to use to find rise times for second order systems. And how you do it, this relates, you can go either way with this. You can go from a rise time to a damping ratio, or you can go from a damping ratio to a rise time. So say you had a 0.78 damping ratio. That would correspond to a rise time, a normalized rise time of 2.4. So that would be TR omega n equals 2.4, which gives you a solution for the rise time, which is 2.4 divided by the natural frequency. So you do need to know the natural frequency to determine this. Okay? Does the chart make sense? Notice that just qualitatively, the rise time increases as you increase your zeta. So as you damp more and more, the rise time is longer and longer. It takes longer and longer for that thing to rise if you increase damping, which is very intuitive, right? If you increase the damping on your system and you suddenly change the input, it's going to be slower to respond the more damping you have. Okay. So this figure is pretty nice. It also appears in the Nice textbook, but it doesn't have grid lines on it. So I find this one to be a lot better. At least the digital one, when you zoom in, it's got nice grid lines. Okay. Good. The peak time has the following simple expression. So this one's actually pretty easy to solve for, where the damped natural frequency is, by definition, omega n times the square root of 1 minus zeta squared. So the peak time is just pi over the damped natural frequency, which is pretty nice. The percent overshoot is related directly to zeta as follows. So the percent overshoot is this expression. So you can solve for it from zeta to percent overshoot with this version. Or if you have a percent overshoot and you want to know zeta, you can use this version. So those are explicit, and they're just percent overshoot and zeta. So if you want to affect the percent overshoot, does it help you to change the natural frequency? No. Percent overshoot is going to be exactly the same as it was before. So if you're going to try to affect the percent overshoot, so these are lines of constant zeta, right? You can't simply go from this pole location to that pole location because they have the same zeta, same percent overshoot, right? You're going to have to increase your zeta, which is to say move to a line that's more that's closer to the negative real axis, that has a smaller angle between between the negative real axis and a ray going from the origin through the pole. So I'm talking like this, like we're going to be able to move these things around, because that's exactly what we're going to do with our closed loop system. In our controller, we're going to move these poles around to have the performance characteristics we want. So for now, we're just, whatever the system is prescribes whatever the performance characteristic is. So like we're given a system, oh, it has this percent overshoot because it has this zeta. But soon enough, we'll be able to say, I want to have a system with this percent overshoot, therefore I'll back out what zeta I need, and therefore I'll put my pole here. So it's pretty cool. We'll get there. And then finally, the settling time is expressed as being 4 over zeta omega n. And then this is another important one to take a look at the graphical representation. So we've got the pole location being there. It turns out that this distance along the real axis is negative zeta omega n. So remember that our settling time, where was the formula for it, 4 over zeta omega n. So if we do, so this is just equal to, well, remember that settling time is equal to 4 over zeta omega n. So as we increase this distance, as we go leftward more and more, this denominator gets larger and larger, and the settling time gets smaller and smaller, right? So if you want to decrease your settling time, you move your poles leftward, more negative in the complex plane, more negative in the real part. So you could draw an arrow and say faster settling. There are 2 T's, I think, in settling. And yeah, so then you could say more overshoot along an arc. That would be another thing you could say. As you go here and you decrease your zeta, you're going to get less, or you're going to get more and more overshoot. Right? Okay, that's all I got. See you on Wednesday.